All right, today we are tackling one of the most important ideas in all of computer science. How do we actually measure how good an algorithm is? Now, it sounds simple, right? But as you're about to see, it's way more interesting than just grabbing a stopwatch.
So let's just jump right in. How do we figure out if one algorithm is faster than another? Your first thought might be easy, just run them both and see which one finishes first. But hang on. What if one's running on a brand new supercomputer and the other's chugging away on a 10-year-old laptop? The time you measure would be totally misleading.
Exactly. The really smart, efficient algorithm on that slow PC might actually look slower than the clumsy, inefficient one on the beast of a machine. So that raw time tells us nothing about the algorithms themselves. It only tells us about the specific environment they ran in. We need a better way, a way to compare them on a totally level playing field.
And it's not just about the hardware. Look at all this stuff. The speed of the computer, the language it's written in, even how skilled the programmer is. All of these things are just noise, muddying the waters. To make a real, fair comparison, we need a special kind of ruler, one that completely ignores all these messy, real-world details.
And that ruler, that special tool, is the idea of analyzing an algorithm's order of growth. So instead of measuring seconds, which we know is flawed, we're going to measure how the running time scales as the size of the input gets bigger and bigger and bigger. This gives us a much more pure and ultimately a much more useful way to compare them.
So here's the key insight. When the input size gets absolutely massive, think millions or billions of items, the part of the math that grows the fastest is the only thing that really matters anymore. Everything else is just a drop in the ocean. That's why we simplify things. We just chop off all the constant factors and the smaller terms because in the long run, they're basically insignificant. We're hunting for the big picture trend.
And this quote right here really puts the stakes into perspective. Choosing an algorithm that grows like n log n instead of n squared isn't just a minor optimization. It is a game-changing, fundamentally different choice. It has a massive, massive impact on performance, especially when your data starts to pile up. It's a deal you absolutely should take, any day of the week.
Now, to talk about these different growth rates like professionals, we need a formal language. And that's where asymptotic notation comes in. It gives us a really precise way to describe the performance limits of an algorithm. It's the framework for how we have this whole conversation.
First up, we've got theta notation. The best way to think about theta is as a tight bound. It's like a precise hug for your algorithm's runtime. It means the runtime is squeezed between two versions of the same growth function. It's not just an upper limit or a lower limit, it's a direct description of how that algorithm scales. It's the real deal. Next is the one you've probably heard of before, big O notation. If theta was a tight hug, big O is a ceiling. It gives us an upper bound. It's a guarantee that says, listen, no matter what happens, no matter how nasty the input data is, this algorithm will never perform worse than this. And that's incredibly useful for understanding the absolute worst case scenario. And to complete the set, we have omega notation. You can probably guess this one. If big O is the ceiling, omega is the floor. It gives us a lower bound. It's a guarantee that says the algorithm will perform at least this well. It's our way of describing the best case performance. Now, this brings up a really critical point. An algorithm doesn't just have one single running time. Its performance can actually change a lot, depending on the specific data you feed it. It can be a speed demon 1 minute and a slow poke the next. This is where we get into talking about best, worst, and average cases. Okay, let's make this real with a super simple example. Linear search. Just imagine you have a big list of things, and you're looking for one specific item. Linear search is the most basic way you could possibly do it. You start at the very beginning, you check the first item, then the second, then the third, one by one, until you either find what you're looking for or you run out of items. So, what's the absolute best thing that could happen? Well, you get lucky. The item you want is the very first one in the list. The algorithm finds it on the first try and just stops. This takes a constant amount of time. We call it theta of 1 because it doesn't matter if the list has 10 items or 10 million. It's just one step. And the worst case, the absolute worst luck, the item you're looking for is the very last one. Or even worse, it's not in the list at all. In that situation, the poor algorithm has to slog through every single one of the n elements before it can finally give up. so its runtime grows in a straight line with the size of the array. We call that theta of n. So what about the average case? Most of the time, you'll probably find the items somewhere in the middle. You might check about half the items, right? So n divided by 2. But remember how we dropped those constant factors? That 1/2 is a constant. In the grand scheme of things, it doesn't change the fundamental growth trend. The runtime still grows linearly with n, so we say the average case is also theta of n. Okay, so now we have this powerful language for describing an algorithm's performance. Let's put it to work. Let's see how it actually helps us make smart, real-world choices when we have different ways to solve the same problem.
Let's go back to our search problem. We can compare our simple linear search with a more clever algorithm called binary search. Now, binary search is way faster. Its worst case is O of log n, which is just phenomenally better than O of n. But there's a catch, isn't there always? It only works if the array is already sorted. This shows us there's often a trade-off to consider.
And that leads us to the next logical question, right? If searching a sorted array is so incredibly fast, it seems like it's worth the effort to sort the data first. But there are tons of different ways to sort data. So how do we use our new tools to pick the right one? And here is the payoff. This is why we did all that work. This table shows 3 common ways to sort things, and the difference is just night and day. 2 of them have a worst case of theta of n squared, while merge sort comes in at theta of n log n. That's that same amazing growth rate we saw was such a good deal earlier. And when you see it visually, the difference is just staggering. For any large amount of data, the gap between n squared and n log n isn't just a small improvement, it's a chasm. It's the difference between an algorithm that solves your problem in a few seconds and one that could literally run for days or weeks. So let's pull it all together. The big idea is this. We have to evaluate algorithms by their order of growth, not just by timing them. Asymptotic notation, that's our O, theta, and omega, gives us the language to do it properly. We have to remember that a single algorithm can have different profiles, best, worst, average. And most importantly, choosing an algorithm with better asymptotic performance isn't just a minor tweak, it's a critical, high-level technology choice. And that brings us to one final intriguing question. We've seen that log n is a fantastic place to be for sorting. It's so much better than n squared. But is that the finish line? Is that the best we can ever hope to do? Or is it possible, under certain conditions, to actually sort things even faster? Now that's a question that opens up a whole new world of even more advanced algorithms. And that's all we have for this explainer. If this helped you finally get a solid handle on asymptotic notation, we'd really appreciate it if you'd hit that like button, share it, and subscribe for more deep dives. Thanks so much for watching.